Good Monday morning radio fans. This video is about the proper practice of listening to a transmitter to see if it's working correctly before putting it on the air. And the fact that I tried this with the TR3 by listening in the Kenwood 430, and what I heard from the TR3 on transmit was so badly distorted with 60 cycle hum that it was almost unlistenable on sideband. We don't just get on the air and say, does my transmitter work? That's a violation of FCC regulations. This isn't CB radio. We're supposed to know that it's correct before going on the air, because going on the air with an improper transmitter is a violation of technical rules. So the way to check this is we put the transmitter into a dummy load and use another receiver right next to it where there'll be enough signal coupled from the coax to the dummy load into the receiver cabinet to pick a signal up on the receiver. And then for these old mechanical VFO radios, we can check the VFO and all that. But when I did that in the Kenwood, listening on the headphones, there was a horrible AC hum. And I know that can't be the filter capacitors in the TR3 or its power supply hiding down here, because that was all gone through with a fine-tooth comb with all state-of-the-art new capacitors and all verified with an oscilloscope. What the problem turned out to be is, if you can see on the bottom of the power strip back there by the wall, the TR3 has a non-polarized AC line cord. It can be plugged in either direction. It's two-prong, and both prongs are the same width. And when I redesigned the power supply, I checked this for correct polarity. I aligned the power cord and I aligned all the secondary connections on the power transformer so they're all in phase to reduce hum. And I'd marked the power cord with a nylon wire tie so the bump was on the what should be the narrow blade side, or L1. I had it plugged in backwards, so I reached down, pulled it out, plugged it back in. AC hum almost entirely gone. And just worked a station in Alabama who said it sounds just fantastic on sideband. Now this old Kenwood's a 12-volt radio. In fact, it was intended to be used mobile. So I'm using an external power supply. But that modern power supply is intended for a 3-line cord and has all terminals on the AC line clearly marked. But if you run into this problem, especially after modifying a power supply, make sure that line cord is the correct polarity. Simply try reversing it. It can't be done with a modern 3-prong cord unless you use a ground buster, but try it. And now for a short antenna topic. I heard a QSO on 40 a couple days ago, one asking the other about getting the match on a Yagi down for a certain part of the band. And the other was correctly stating that if you want a lower response, if you want a lower SWR at a lower frequency, you got to lengthen the elements. Now, what they didn't realize is that there are 2 matches for an antenna, not one. And to illustrate this, and I've done and proven all this here, using a dipole with the so-called coax lines. And if you'll see my antenna videos, you'll find all this information. But there's a match between the transmission line and the feed point, which establishes the R value. 50 ohm coax needs a 50 ohm feed point. That 50 ohms is established at the feed point by fields coupling from the wires where they exit the transmission line to the outside of the transmission line and down to the ground. And that coupling out of the line down to the ground is what sets the R value for a dipole. But there's also the length, and that has to do with the quarter wave time long dipole arms and the time needed for that energy to go to the end of that wire and reflect and come back. And that must be 180 degrees, 90 degrees out, 90 degrees wire length, minus a little. And then that process of reflection, that's what causes emission from the wire. If that wire is the wrong length, then those forward and return energies are out of phase, and there's energy left over on that return wave back at the feed point, and that's what couples down a transmission line and becomes reflected power. So if either of those are off, there'll be a mismatch, and it may not be enough just to change length. So how do we check this? Well, if we use an SWR meter, and if the antenna system is otherwise correct, we're not trying to do something dumb like put 300 ohm line on a dipole, because 300 ohm line cannot possibly match a dipole. Never. Then change the transmit frequency, watch the SWR indication, change the length here and there. Note what frequency the SWR indication is the lowest. That corresponds with the frequency that corresponds with the length of the antenna elements. Let's say that the best that can be had is a 1.5. That's not a very big number, but that represents the difference of a 50 ohm line connected to a 75 ohm antenna, and it's a big mismatch. But if the minimum available by changing frequency is a 1.5 or 1.3 or whatever, that's probably feed point mismatch. And with a dipole, that's changed by changing the antenna height. With the Yagi, it could be interaction with the tower or effects of height from the ground, which makes it difficult to change because Yagi is fixed by the height of the tower. It could just be a poorly designed, too short loaded antenna that's a compromise for too many bands. It may not be possible to fix it easily. But if there's a residual SWR, if you will, after changing the length of the elements, then it's either going to be because the elements aren't the same length, they're not symmetrical, or it's most likely a feed point mismatch. And there's a difference between the feed point match and the match, again, due to the length of the elements. Length of the elements is easy to change. It's just mechanical. The feed point can't be changed. It has to be matched. And for example, that's why I have the aluminum boxes back here with the big 75 ohm line there going into the plastic nut. That's 75 ohm line. The connector is a 50 ohm SO to a PL 50 ohm. And that's a 50 ohm side, and there's an L matching network in there. And an L network can be put at the feed point to correct and more or less eliminate that residual SWR. And believe me, it makes a huge difference. If you got a lot invested in a Yagi and you find feed point mismatch, it's not rocket science to make a relay box to switch in various L networks. The way to do that would be to get a measurement of the R value at the feed point at that minimum SWR frequency, which presumably is just a resistive mismatch. And if it's 75 versus 50, get in the ARL handbook and look up the formulas for calculating an L network. It's also in Radio Engineer's Handbook by Terman. And an L network is just two components. Wind your own toroid coil, get some low loss RF capacitors or air variable, and make an L network. And it makes a big difference in the performance of the antenna.